Welcome to episode 13 of the Quantum Science Seminar, and today is going to be all about quantum computing, but in a very different way than we had before. And we do take your questions. Please send those questions to us via email using our account at quantumscienceseminar@gmail.com, or you could use the YouTube live chat at the right or at the bottom of the screen. We're going to take a break in the middle of the talk to start answering some of your questions, and then answer the rest of the questions at the end. And our speaker again today has very kindly agreed that if there are more questions than we can answer in the time we have, that he will provide some answers in written form that we will then put on our website later. With this, I'd like to remind you also that you have a 30-second time delay between what you're seeing and what we're doing here. So please take that into account. And with this, I would like to hand over to Valentina, who will introduce our speaker today.
So it's a real pleasure for me to introduce Olivier Pfister today at the Quantum Science Seminar. And so when I asked Olivier to point out the main step of his path from a PhD in molecular spectroscopy in 1993 in Paris to the quantum frequency comb today at the University of Virginia, so he told me that he's really proud of his postdoc at GLA with Jan Hall, when he really pivoted from laser spectroscopy to quantum optics, because Jan was the right person to let him to do it. And then the postdoc at Duke with Dan Gauthier, where he was really a fun for him to make a two-photon laser. And then since then, he worked on entangling the comb ever since, but which is really hilarious, he said, because a comb normally used to entangle. And for which also, he's really proud because he was nominated as APS Fellow with the DAMOT in 2013. And so I'm really happy to have Olivier here today. And Olivier, thank you. And the stage is yours.
Thank you very much, Valentina. Thank you very much, Sebastian and Christian, for organizing this. This is an awesome seminar series, and I'm really thrilled and honored to be part of it. And I hope you will not regret looking at number 13 of the series. So this is about quantum computing over the rainbow, as I call it, and it's basically how to build a quantum computer with light. And this has been my life for 10, 15 years now. We've had funding from the National Science Foundation and episodically from DARPA when they feel like it. You have my website down there if you're interested in knowing more. This is the group as the present day. There's two postdocs, Raphael Alexander, who left for Carl Cave's group. He's been at New Mexico for 3 years now, but we're still working together. And Awin is now with Alberto Marino at Oklahoma. He was an experimentalist with us. Raf is a theorist. Carlos is with us presently. He's a theorist. So we have extensive collaborations with theorists, even though we're an experimentalist group. We like to do both, or delude ourselves in thinking that we're doing both. But Carlos is a real theorist. Raj is graduating next week, and then moving on to Alireza Marandi's group at Caltech to do some coherentizing machines and things like that. Chun-Hong and Catherine are next in line with Miller, and they're all working on their project and nearing completion. So we have fun collaborating with a number of people. Avi at Bar-Ilan University in Israel, Paolo and Marcelo at the University of Sao Paulo, Seunam and Thomas Gerritz at NIST for the photon number resolving measurements. We have a very exciting venture at the University of Virginia with the engineering, electrical and computer engineering guys, Joe Campbell, which one NIST guy calls the Pope of the avalanche photodiode. And so I'm very, very thrilled that I was able to attract his attention and his interest. And so we're trying to work on photonics, quantum photonics. Xui came from Kerry Vahala at Caltech, and he has been working as a junior faculty for a couple of years at UVA. And Andreas is Joe's heir apparent quantum photo detection, also in integrated optics. So we're trying to put everything I do in free space with what they do in integrated optics and try to come up with cool devices. And there's the theorists row here. Myung-Shik and Leandro and quantum optics, quantum information. Nick Minicucci is a long-time collaborator. Ever since he was a grad student, we've worked together, and it's been a thrill. We have organic ebb and flow kind of things, and sometimes nothing happens, and then boom, we start working again together. Raf is Nick's first grad student, and he's a fantastic scientist. And so we work together as well. Israel is a condensed matter theorist, brilliant guy that we're lucky to have at the University of Virginia. And Simonetta is a theorist in nuclear physics. And so you can guess that these two guys would talk about quantum simulation with them and try to see how what we do can be useful to them. So today I will talk about the first two bullets, large-scale cluster state entanglement. I will explain a little bit. So basically how we claim we want to make a quantum computer with light. So I will explain why we claim that. And that goes first through understanding what a cluster state is. Then also quantum engineering, quantum state engineering and characterization. And that's relevant to quantum error correction, but I will not talk to quantum error correction because we haven't done that yet, but we're working on it. The quantum photonics on chip, I mentioned that I'm not going to talk about. The quantum simulation of nuclear and condensed matter physics is also things that we are interested in. My talk will have two halves. Hopefully there will be half and half, we'll see. The first, and it's about, keyword is a Gaussian and non-Gaussian, and that refers to the Wigner function. So the Wigner function is, I'm going to talk about this in the second half of the talk. The Wigner function, just without insulting those of you who know what it is very well and use it all the time, but just so that everybody knows what it is in case you don't use it all the time. The Wigner function is a function of both, for example, position and momentum, and it's a function whose marginals give you the quantum probability distribution in the other variables. So if you integrate over momentum, you get the probability distribution density over position and vice versa. So it's the only possibly defined function that does that. And it looks like then it's a joint probability distribution. And that's the classical meaning of the Wigner function. And for pure state, if it is indeed the case that this function is a positive function, because that's what a joint probability distribution must be, then it has to be Gaussian. It's a Hudson theorem. But quantum mechanics does not require the Wigner function to be positive. It can very well have negative parts. It's not a problem at all. For example, Fock states have Wigner functions that are not positive, and therefore they're not Gaussian. And then so for pure states, so when I say Gaussian, non-Gaussian, there's this idea that the Wigner function is all positive if it's Gaussian. Doesn't mean it's a classical state. Squeeze states have Gaussian Wigner functions, but it means that you don't really need quantum mechanics, because you could have an ad hoc addition to classical electrodynamics to explain squeezing without invoking quantum mechanics, and still, because the Wigner function sort of provides a local hidden variable description, if you will, of the quantum fields, and therefore you can't violate Bell inequalities. As soon as the Wigner function is non-Gaussian, it's a pure state, it's also negative, and only quantum mechanics can explain that. So there's been some sort of deep origin of quantumness in the Gaussianity, non-Gaussianity of Wigner function for a pure state. Okay, so I've thrown at you a lot of stuff, but the bottom line is that Gaussian quantum optics is about fields. It's a wave nature of light, and non-Gaussian quantum optics is about working with Fock states and photons and counting photons, correctly without error, which is hard to do, and that's our work with the NIST folks that we'll talk in the second half of the talk about. Okay, so quantum computing in a nutshell, very, very simple. There's, for universal quantum computing, that the kind of which we can expect exponential speed up, there's kind of two main flavors. One is the circuit based. So you've seen a circuit model, which you've seen before. You have initial quantum states that are in a product state. They're all independent. And then you have the universal gate set in a circuit, which is any kind of single qubit gate and or generators thereof, and one entangling 2-qubit gate, such as the C0 here. And for example, and then some measurements and some feed forward to other qubits, and that's a teleportation circuit that you have here. Website goes from this qubit down to that qubit when all is said and done. There's another paradigm for quantum computing, which is the measurement-based quantum computing. In particular, one-way quantum computing, which was invented by Robert Rasendorf and Hans Brigel, and generalized by these guys for continuous variables. And so I'm going to explain the continuous variable business in a little while. For now, I'm going to stick with qubits. And the idea is that you start with all this on this diagram. All these symbols are, qubits. For example, spin 1/2 qubits, and you have to establish them initially in a cluster state. And the cluster state is basically a entangled, multi-purpose, generic entangled state that contains all the entanglement you'll ever need for any quantum algorithm. And once you have that cluster state, things will proceed by measuring qubits one by one, single qubit measurements, and then feeding forward to the neighbors on the graph. So the notion of graph is important here. And the cluster states are basically, each qubit is in a superposition of 0 plus 1 over root 2. And in between, the edge denotes a control Z gate. Okay. And these commute, so they can be applied in. So if you can build a big cluster state like that, then you measure one qubit and it will change the rest in a way that's defined by the measurement basis and the measurement result. The measurement result is random, but like for teleportation, it doesn't prevent the process to be fully deterministic, because you have the measurement result and you can feed forward to the other qubits based on what the measurement result was. So you can adapt to any situation. So there's no, even though there's randomness, there's no probabilistic nature to this. It's entirely deterministic. Okay, so here's an example of teleportation. If you have one qubit in that initial state psi, and then another qubit in this plus state, 0 plus 1, that we use for cluster states, you apply a CZ gate between them. And then what happens is that you just measure in this plus minus basis here, right? So it's just a visualization of all the calculations. I don't go through the derivation. But if you do that, you find either plus or minus, which is little m equals plus or minus 1. And you can calculate that this qubit is now in psi with this Z Pauli operator and the Hadamard operator applied to it. So what do you have to do? Well, you can just undo that by applying those things. That's the feed forward. And you're left with psi. So you have a teleportation. And that's an example, the simplest example of measurement-based quantum computing. But really, measurement-based quantum computing, one-way quantum computing, is a generalization of teleportation. This is what it is. So if you understand teleportation, that the teleportation is 100% deterministic, it works. There's no caveat or anything about post-selection and exponential cost to that. There's no problem with that. So one-way quantum computing works the same way. For example, here's just more cartoons to show you how it works with a 3-qubit cluster state, linear cluster state. If you measure the Z, so let's say it's in a computational basis, you measure 0 or 1, and then you feed forward, although that's not super important in that case. You break the state. Okay, that's not super original, but if you take the same state and now you measure X, measure the spin along X, so you measure the plus minus basis, then now the feed forward is important, you end up with a bridge state. So you create entanglement between the extreme qubits that didn't exist before. And you can go crazy with that. You can take a more complicated graph, measure the central node here, do feed forward, and you get that stuff. So the cluster states, it's an old concept now, but they work really well. And they allow you to shape the cluster state with measurements. So you can process, implement quantum gates, teleportations, and you can, Rasendorf and Brigel explained, you can implement the universal gate set on cluster states if you have a square grid lattice. right? So if you have a square grid lattice, so it's very different from building a quantum computer with circuit model where you have to focus on, implementing gates from qubits, and you still have to do quantum error correction in every case, of course. But in the cluster state model, you have to, once you have the cluster state, you're a long way down, right? Because the measurements are easier to do. Measurements are things that we do in the lab all the time. We're very good at that as physicists. We're very good at measurements. So building gates and entangling things is the hard part. And so if you build a cluster state, you set yourself up really nicely with a universal quantum computing substrate to play with measurements and feed forward. So that's what we've been focusing on. And now we do Q modes, not qubits. So we do continuous variables, not discrete variables. Okay, so I'm not going to spend too much time there, but I've written and then there's lots of papers and a lot of references in that review paper that I wrote about that you have at the bottom. Certainly it was proposed in 1999 by Seth Lloyd and Sam Brownstein. And the idea is that you replace your qubit computational basis with a continuous one, think position eigenstates or amplitude quadrature eigenstates of a quantized electromagnetic field. And the canonically conjugate, one of the canonically conjugate, because this is a spin, so there's 3 of them, but let's say SX eigenstates obtained through Hadamard transform map onto the canonically conjugate. There's only one of them, which is the position in 1D, the momentum in 1D to position, which is the Fourier transform. So you have this analogy that builds up. You have the Bell state, you have the EPR state, and you can go on like that, the Pauli state of Heisenberg group, and this is all very well defined. And it looks horribly complicated. And so you're very well justified, to ask the question. This is Jon Stewart. He's internationally known, I hope. We sure miss him here. I think he was burned out when he left the Daily Show. Why? Because it scales. So why does it scale? Well, because we can use quantum optics. We use quantum optics with quantum fields, and that's why we have continuous variables. These are the amplitude of the electromagnetic field. So this is the Gaussian part of our things. So this is the relation to the quantum optical frequency comb. Really, this is the set of modes of a cavity of an optical resonator. That's what you can call the optical frequency comb. Of course, the optical frequency comb is what you get when you put a linear gain medium that's broad enough to be multimode and excite actually a record number of modes, millions of modes, hundreds of thousands, right? And of course, Jan Hall and Ted Hench were the pioneers of this, and this has been fantastic for the past 2 decades and revolutionized metrology and precision measurements. And we want to use that for a quantum computer. So what's the difference? Well, the difference is that in a laser, you emit photons stimulatedly, but one at a time, into the resonant modes. Now, we're going to take the same cavity, but we're going to change the 1-photon emission medium with a 2-photon emission medium, make that an optical parametric oscillator, which is like that. So there's no excited state, real excited state, it's all virtual. So you annihilate a pump photon and emit a pair of signal photons. And then what happens is that in a comb, you emit photons in pairs. And when you emit photons in pairs, you create quantum correlations. And we are not looking at individual photons where, so in a given field, there's many pairs that are emitted there. And so there's a quantum amplitude correlation between this field and that field, and between this field and that field, and between that field and that other field, right? And that creates Einstein-Podolsky-Rosen or two-mode squeezing, Einstein-Podolsky-Rosen entanglement. And the question is that if this guy is entangled with that guy, and that guy is entangled with that guy, and that guy is entangled with that guy, what does that tell me? Well, if you go with bipartite entanglement step by step, you don't have transitivity. You have to, solve the whole problem, write the Heisenberg equations for the whole thing and see what you get. And so we started doing that. But the bottom line is that you get multipartite entanglement and you get a cluster state. And that's what took us a while. So it's not obvious. It took us 5 years to figure it out. In 2004, I started realizing that getting those things, so that's the first time we did that. I just got tenure and I decided to stop doing things that are useful and start doing crazy things, and at least to me, and started getting those kind of things, this kind of graphs where everything is connected with everything. And that's not useful for quantum computing. Those graphs are too connected. This is a GAZ state. It's a cluster state representation of a GAZ state. For quantum computing, you need sparsely connected graphs, like square grid, triangular lattice actually work, hexagonal, Kagome, all these guys work. These are too connected. But okay, we started realizing that if each of these dots here is a mode in an OPO, in an optical parametric oscillator, then you could grow these graphs just by having the right nonlinear two-photon emission engineered the right way inside the cavity. Right? And so then I met Nick Menicucci and Steve Flamia. Nick was an undergrad with Carl Caves, and then he moved on to Princeton to do string theory, got bored, and stayed a Princeton grad student, but moved on to work with Michael Nielsen at the University of Queensland. And then that's when I met him, and then he introduced me to Steve Flamia, who was a graduate student with Carl Caves. So I have unrepayable debt of gratitude to Carl Caves for forming all these young, brilliant minds who got interested in what I do. And then we realized in a single OPO, you can actually create that kind of graph, which is a square grid lattice, which is wrapped into a tube and wrapped around into a torus because of some boundary conditions that are used because we use a single OPO there. There's some detailed structure there. This is all feasible in the lab. But we found a much easier way to do this. And so we started doing experiments. In 2011, we started creating those entangled states. These are cluster states. They are just 4-mode cluster states. And they are distributed in the optical frequency comb like that. That was Matt Peischer's work. That was picked up by Joanna Miller in Physics Today. And then in 2014, we had the demonstration of the same 60 modes that you saw on the previous picture, but now all entangled together. And this is it's a cluster state. So if you measure that guy, it's going to disentangle it from the rest, but the rest is going to stay entangled. That's the big thing about the cluster state. And you could make them one big 60-mode cluster state or two 30-mode cluster state, or distribute different ways. The reason why we had 60 modes is because we could only measure 60, but I think the phase matching bandwidth is actually 10,000 modes, but we haven't measured them all. We're working on a different way to do that. It was kind of technically difficult for us at the time. This is what the experiment looks like. There's an optical parametric oscillator here, as promised. There's some pump lasers that are phase locked together. There's a local oscillator laser that's phase locked to the pumps. There's some filter cavity locks, so there's boundary over hole locks and phase lock loops all over the place, and some entanglement verification that uses multi-tone homodyne detection. And I'm happy to go into the technical details, but I just want to give you an overview there. So I'm going to skip them for now. Basically, you can look at this as the interference of two optical frequency combs, because they have two different polarizations in the same cavity. You saw there were two crystals in this bow tie OPO, and one makes a comb here for one frequency, for one polarization, and that's the frequency axis. And there's another comb here for another polarization. And basically, we interfere them together, and that's what creates all those two-mode entangled states that are denoted by the dashed line. Interfere with a beam splitter and gives you that long cluster state. We didn't do it in the lab, but proposed a way to create a more, so if that cluster state chain is schematized like that, I skipped the details, you can actually make a square grid like that, interfering 4 OPOs or 4 combs. Since then, there's been also very nice work on other continents. So in Paris, the group of Nicolas Treps and Claude Fabre showed that with an OPO pumped by not just one frequency or two like we do, but with a comb of frequencies, you get very interesting results, and you get a very versatile and configurable way to create entanglement, multimode entanglement in the frequency comb as well. In Brazil, in São Paulo, Marcelo Martinelli and Paulo Nussenzweig showed that above threshold, you can actually also create multipartite entanglement. They showed hexapartite, but in fact, I think it scales to larger. I think they have several hexapartite states, in fact, in that experiment already. And there's another way, which is to use, I'm going to briefly touch upon it because it's been in the news recently, using a temporal modes instead of frequency modes. And still like a comb, but now you look at, the OPO output is pulsed. And if you do that, there's a way to entangle everything into same kind of cluster state. So the way it works is that you have a squeezer here. It makes a squeeze state. So this is the phase space, the amplitude quadrature, Q-like, position-like, and the momentum-like quadrature. And you have a squeeze state this way. You see that the quantum noise ellipse is squeezed. And here there's another squeeze state that's squeezed along the other quadrature. If you interfere them, those single mode squeezers are two-photon emitter, the same as the ones we use, but they emit the two photons in the same field. They degenerate. So they only use one mode, whereas we use a lot of modes because we put photon pairs into lots of non-degenerate fields. In that case, you have this frequency here interfering with that frequency there in two quadrature canonically conjugate squeeze states. And what you get here is an EPR state. So you get this two-photon now emission at the output of the beam splitter. And if you delay one of the arms, then you get those entangled pairs. These are temporal modes now, and one is behind. And so this guy interferes with the previous guy that went forward with the beam splitter. And the interference of those guys like that together creates the same cluster state almost as the one that we use in the frequency domain, where we had the two comb interfere, but are frequency shifted. Here it's time shifted instead of frequency shifted. Furusawa group in Japan did that. They had 10,000 entangled because it's all in the time domain. So they had two at a time. Every 45 meters, there's another one coming. So the lab is not big enough. You have to do it one after the other. You have two detectors waiting, and you use the same two detectors to measure everybody. And that's fine. It's a viable implementation of a quantum computer. You can show it's a Wallace and Gromit model. And they improve that to 10 to the 6, so 1 million modes, just running the experiment long enough that it's stable enough that you can keep measuring. And basically you build up your cluster state and your chain unfolds in time, and eventually you can measure 1 million modes. And more recently, science decided that cluster states are cool. So they started publishing cluster state papers, and Akira Furusawa's group had a square grid cluster state. So that's a big achievement because, as I told you, the square grid cluster state is a universal quantum computing because it allows you to implement the universal gate set. At the same time, a former postdoc of Furusawa's, Jonas Nygaard-Nielsen, who joined Ulrik Andersen's group in Denmark, also showed a two-dimensional cluster state. So that's really exciting. This is what's brewing in my lab. I'm not going to tell you much more about this, but we're going 3D and beyond because we realize that really it's not necessarily the good way to start with one and then increase. Sometimes it's easier to start with higher dimensions. And so this is our inspiration there entirely for this. And the 3D cluster state is interesting because the 3D architecture of a cluster state was shown by Robert Rasendorf to enable the encoding of the surface code, the topological error correction code invented by Kitaev. And so it's not the entire story for quantum error correction. You still need non-Gaussian resources. So this is entirely Gaussian. So, but you can get some measure of fault tolerance doing that. So this is something we're willing to explore. And so the take-home message for this, and this is going to be the first half of the talk, where the Gaussian part is completed, and the generation of sophisticated quantum computing universal cluster states on a very large scale, thousands of Q modes, even millions, is easy. That's the message I want to send over continuous variables. So the price to pay is that you have to deal with continuous variables, which are these position momentum-like variables. But the good thing, the only reason we're doing that is because of scalability. And also, because it's optical, we can probably translate that to integrated optics and photonics at room temperature. So I'm happy to take questions at this point before I dive into the non-Gaussian part, if there are any.
Yes, we have some questions, and let me start with the first one by Bill Phillips. And that's about, it just links with your last part a bit, because you mentioned error correction again. And could you elaborate a bit more actually how error correction really works, and how you can build actually logical qubits out of your physical continuous variable qubits?
Hi, Bill. So this is coming in the second part.
That was an easy answer.
So the reason, but the reason Gaussian states and gates it's been proven. There's a no-go theorem for violating Bell inequalities. There's several of them by different people. Violating Bell inequalities, that's by Bell. Distillating entanglement, that's by Isert and Plenio and others. And doing quantum error correction by Nicolas Cerf and Benjamin Nizet, I think. I hope I remember his name correctly. So it doesn't work. So you have to have non-Gaussian resources. And non-Gaussian resources, and also they are needed, non-Gaussian resources are also needed for exponential speedup and universal quantum computing. So they are needed. They're the equivalent of non-Clifford operations on qubits. The difference is that for qubits, non-Clifford gates are needed for exponential speedup. It's a Gottesman-Neal theorem, but they are not needed for quantum error correction. So there's the difference between continuous variables and qubits here. I think it's because we're working with wave functions rather than discrete state amplitudes. But nonetheless, so what do you do? Well, you could use cubic nonlinearities, which is hard, or you could use photon number resolving detection, which project into the Fock state basis, which are non-Gaussian states. And that's really, and actually the two have been linked by Gottesman, Kitaev, and Preskill in their 2001 paper encoding a qubit in an oscillator, where they showed that you can generate cubic field evolution, also known as a cubic phase gate, seeded by the cubic phase state, by using Gaussian entanglement and photon number detection. So I'm going to say more about that in the non-Gaussian part.
Okay, good. So there's maybe one more, and that is a question about if there are tricks such as using topological photonic phenomena to boost basically the stability, for example, to create photonic cluster states.
That's a great question. I think it's possible. What I've seen from topological photonics is that it's very lossy in the implementations. So everything that we do has to be with extremely low levels of loss, right? So at the end, and it's not very often I hear, you know, squeeze state are fragile versus loss. No, there's a fault tolerance threshold for everything. You know, people who build quantum computers with trapped ions or superconducting qubits, everybody knows there's a fault tolerance threshold there, 1 at 10⁻⁶, 10⁻⁴, 10⁻² if you do topological error correction. So these are well known. These apply to our implementations as well. And so there's some minimum levels of squeezing that are required. And so that was a tangent. On the topological photonics, I think, yeah, these are new concepts. These are interesting things. If they can be made low losses, that could be fascinating to explore.
Okay, I think let's go on for the second half, and the remaining questions come at the end.
All right, thanks. So on we go with the particle nature of the business. And so it's all about photon number detection. And these are the guys, Sewunam, who started the whole business and is known worldwide for providing the world with photon number resolving detectors. Aaron Miller was, he's now founded quantum opus, and he was a faculty at Albion College when we started working together with Sehu. And so the idea is that you want, to create a POVM set that's exactly the projectors on the Fock state basis. Right? And so the device here is a superconducting transition edge sensor, and it's here in our case it's tungsten. It's a very cold little bit of chip of tungsten. It's 20 micron by 20 microns. It's coated so that it makes a little optical cavity. So when a photon is delivered to it via fiber, single mode fiber, the photon actually bounces inside the tungsten until it is absorbed. So it is a resonant cavity at the wavelength of detection, and then that brings your detection efficiency up to, well above 90% system efficiency. And then when the photon is absorbed, that heats the TES a little bit, and so this is the resistance versus temperature. I said this thing was tungsten was superconducting. So this is the resistance of tungsten schematized, right? It's a normal state, metallic state has, its resistance still drops with temperature, but okay, it's kind of flat here. And then when it hits the superconducting transition, it drops like a stone to 0. And so you bring this guy, we operate them right here at the bias temperature. And so the photon heats a little bit through absorption, the energy transfer, and then the resistance climbs a little bit. On that steep slope, it makes a very abrupt change that can be detected by a squid device. So mutual induction interferometer, basically. And if you had two photons, you would have like two quanta, and the heating would give you twice the jump, 3 times the jump, and you get a signal which is like that. Once the signal is there, there's a cooling because the thing has to go back to its temperature. But the peaks are different heights depending on the photon number, right? As long as you're on your slope. If you're too many photons, then you get out of the slope and then you lose the resolution, right? But you can still see interesting things. So this is another signal. These are signals that we get, all the signals that we get in our lab. So these are different peaks. Now we pulse our light to get the photons at the same time. So you have 1, 2, 3, 4, 5, and that's at 1064 nanometers. That's about how many photons can fit on the slope. And if we get that distribution there, we can build a histogram. This is in the log scale. So the probability of 0 photon, because we have pulse, we have timestamps, so we can tell when we look, when the pulse tells us when to look, and if we have 0 photon there, that's the vacuum state. 1, 2, 3, 4, 5, up to 6. And we can build a probability distribution, which is the photon number probability, which is very, very useful. And I'm going to show you what we do with that. So with this transition edge sensor, we can actually perform photon number resolved measurements. Now, they better be at 100% quantum efficiency, right? Because if you think, you see 2 photons here and you think it's a 2-photon state, but no, it was a 3-photon state that lost 1 photon. Well, you know that the 3-photon state and the 2-photon state are orthogonal, so it's a disaster. So you can't really use that for anything. So you must have photon number resolving detector, must have photon number resolution to discriminate between different photon numbers. APDs, avalanche photodiodes don't do that because they give you more or less the same avalanche whether you had 1 or 2 or 3 photons, although the experts can tell you there are differences and they can work them a little bit, but it's hard. It's very hard. The TS is much better in that respect. It's amazing. If you have more than 5 photons in our case, you see that, well, it climbs up the TS slope and then it goes into the normal regime, but then it takes a longer cooling time if you absorb more photons. So we get these signals that saturate at the 5-photon height. But if you had more, then, if you had fewer photons, it will go back sooner than if you had more. And you can see that between those different, between those different guys, they actually can be separated. And in fact, the people like Andrew White at the University of Queensland showed that at 820 meters, 20 nanometers, they could distinguish up to 15 photons, even though they had probably like 4 on the slope, right? So, but you have to do signal processing with FPGAs and things like that, but integrate the signals and look at the areas, for example, or things like that. but it's possible to. So then you can, get up to 10, 20 photons per TES. If you multiplex them, you can probably count up to 100 photons. And that's really, really, really interesting. So, okay, back to this. This is the inside. This is Aaron, when he came to us, installed the TES. We got an NSF grant to work with CEU, and they built us our system. You see the little tungsten chips are inside there. Instead of those little things there, and this fiber coupled. This is really a feat of engineering because it has to stay stable when you bring in from room temperature down to 100 millikelvin. So, things can tend to shift and move and thermally contract. And these still work well. I'm going to give you just, I'm going to run out of time very soon. So I want to still reserve time for questions. So I'm going to go a little bit faster here in terms of what we do with photon number resolution detection. And what we do, we've done a lot of Wigner function reconstruction and quantum state tomography. And then I will explain how we can build those Gottesman-Kitaev-Preskill states that are useful for quantum error correction, which is, Bill's questions about how we can use them on the cluster states, the scalable cluster states that we have. So, and everything is needed to have the device. So the Wigner function, whose marginals give you the probabilities for position and momentum, like I showed earlier, can be written like this. This is a density operator here. And these are position eigenstates, shifted opposite directions, integrated over the shift with a phase shift there. So it's kind of it's a very, once you stare at it long enough, it starts making sense. But initially it's a little bit hermetic. That Wigner function is a unique characterization of a quantum state because it is a unique relation to the density operator, can be non-positive, and also has this property. If I write Q plus IP as alpha, complex parameter, I can write this as a trace of this thing where you have rho here. So it's the expectation value, trace of rho times this operator. So expectation value of this, which is the displaced photon number parity operator. Okay, that's the Royer theorem. And it's, to me, it doesn't say anything as an experimentalist until you apply the cyclic permutation of a trace, so that guy can move around to there. And then when you have this, you have the trace of the photon number parity operator, so averaged basically over rho displaced by alpha. So the state that you want to measure, you can displace it in phase space. Alpha is Q plus IP, so QP phase space. What does that mean? It means in optics, you have an optical state. It's going to have to be controllably displaced, shifted in position momentum, i.e. in amplitude and phase. That we can do in the lab. So I can get any kind of quantum state. I do some phase shifts, some amplitude shifts, and then I measure the photon number. And I reconstruct the expectation value of the parity of the photon, -1 to the n. So I showed you how we could get a photon number probability distribution with TES detectors. So we just had to build a amplitude phase shifter, and that's what we did. And so we decided to do that. And so that's something we published last fall. We had an OPO, which is basically a source. It's an OPO way below threshold, way below threshold. So that it's really a lot. The OPO in the previous part of the talk, the first part of the talk was below threshold, but it was near threshold. So it's very weak light, but it's a lot of photon pairs at a time. Whereas here is only one photon pair at a time ever. And one of these photons goes there, gets filtered the heck out of, we filter the heck out of it, and we send it to a TES detector, and that heralds the twin. And the twin goes to the tomography. So it heralds a single photon state. And we do tomography of that because it's interesting, because we did that for coherent state before, but now we wanted to see the negativity of the Wigner function, which goes away when you have losses. And so we have the displacement set up here. There's a laser that's amplitude modulated and phase modulated with an EOM and a piezo. And then superpose to the quantum signal with a very unbalanced beam splitter that reflects 99% of a quantum signal and transmits a little bit of the coherent state. And that is exactly, that's a pretty good approximation. Not exactly. It's a pretty good approximation of a displacement operator. And then we send the whole thing into a TS and we count. We count, we reconstruct the probability distribution, and we calculate the expectation value of the parity operator. And these are the heralded photon signals. So if we have one heralded photon here, we have the twin there. These are sync tracks. And all those guys are happening at different frequencies. And so the filtering just kills them because we only look at the ones that have exactly the same frequency so that they can have also the same frequency as the displacement field. So that's a very, very tight frequency stabilization constraint that we had to fulfill. Okay, we have a 58% total heralding ratio. So it's a probability of seeing that guy if we have this guy here. So it's not, we'd like this to be 100%, which means that 42% of the time we see that here and there's nothing there. So that's vacuum. So that's vacuum contamination. So that's not so good. But be that as it may, with 58%, we have the Wigner function reconstructed for a single photon state, which is okay. You know that it's supposed to be looking like a crater, a volcano with a crater negative in the middle. And this is what we get. We can only displace that far, so we don't get very far away over the lip of that Wigner function. And there's a little bit of error there in the high value of the displacement. But the key point here, the really crucial, and these are raw data, there's no correction for anything. There's no inference of losses or anything. It's just what we get, what we can reconstruct from the raw data that we get from the detector. And we see clearly a negativity of a Wigner function, which we then infer as to be fitted, once fitted with a mixture, statistical mixture of the vacuum state, the 0 photon state, and the 1 photon state, gives us 57% of 1 photon state, which agrees with the 58% of heralding ratio that we have characterized experimentally. So we were happy because this is the first time that we can see negativity like that in the photon counting experiments without any correction, without any trick, without any, it's a phase sensitive experiment, but since then we have improved that greatly. And this is gonna go way too fast, but we have invented a new way to, we have generalized that displacing, so this is a quantum state that you measure, and this is a displacement field, which is amplitude and phase modulated. And remember, that's this very unbalanced beam splitter. This one transmits practically everything and reflects a little bit the field that displaces quantum state. Now we made that beam splitter 50-50, which means half the light here in what we want to measure is lost. And we do an overlap with, again, a coherent state that's modulated, shifted in a calibrated, controllable way. But now what we get here is basically the fidelity of this guy and that guy. It's completely messed up. It doesn't look anything like this state, but it contains everything we need to reconstruct accurately the density matrix. Rather than the Wigner function, it's going to be the density matrix. There's a lot of theory there as to what that overlap is analytically. We've done all that. It's all in that paper, which is on the archive. And I forgot to put the archive, but it's last year. The performance of this, the reconstruction uses semi-definite programming by inverting matrices in Fock space. And so it's not a Wigner function reconstruction, but it works much better. In particular, it can deconvolve losses that are known. So if they're not known, that's a different problem. But here we had a 50% heralding ratio. So that's the basically 50-50 of vacuum and 1 photon state. So not looking very good for the Wigner function. But if we do the full protocol of that coherent overlap tomography, we are allowed to deconvolve the losses completely as calibrated with our experimental setup. And when we get the full negativity, and you also see that we get well over the lip with displacement by a coherent state that are even smaller than in the previous realization. And once we average over all the phases, we get, which is usually done in all Fock state measurements in the past because of the cylindrical symmetry in phase space, then we get a very nice result. So that tomography method, again, I'm rushing through this because it's too much to say, but this is an extraordinarily good characterization tool for any kind of quantum state. So now we're getting into quantum state engineering. This is what Bill's question was about, the GKP states, which are one way. It probably isn't the only way, but these are non-Gaussian states that are basically, that look like combs, but not in frequency, in phase space. So versus this is the wave function in Q, the amplitude quadrature wave function of a Gottesman-Kitaev Presqu'île and Scylla for error correction. And you see that it looks like a comb. It has spikes at lots of different values that are separated. And if you Fourier transform a comb, of course, in the P domain, you have the reciprocally spaced comb, which is that guy. And so that state is extremely exotic. You can use it as a qubit encoding over the continuous variable of the quadrature operators. And you just shift that thing so that it's same spacing, but shift by half the spacing, and you have a logical 0 and a logical 1. And this is one method. And Nick Menicucci has looked at this encoding and determined that you don't need more than 20 dB of squeezing to reach 10 to the minus 6 error rate. And so it's actually less than 20 dB to reach 10 minus 4, 10 minus 2. And so the way it would work is that you'd have those blue guys there, which are GKP and Scillas, and everything else is the cluster state that I showed you. It's the square grid lattice. And those guys have to be fused to the lattice at different strategic points where you want to do a syndrome measurement and subsequent correction. And so you have, like, for example, cluster state gates and things like that. And this is the model. So a lot of people are working around the world. And I'm just going to flash this, but we have Miller and Raj have worked on what to do if you have single photon states, coherent states, and you do the kind of generalized experiments to what we do with tomography, with photon number resolving detection, and this kind of engineered projections. And this is a probabilistic scheme. So it's not a highly efficient one, but it's a way to generate a GKP state out of no squeezing here. It's just single photon ancillas and coherent states and photon number detection. With that, I'm gonna close just with one thing that we're working on right now. This is a long-term prospect for us. We're working on quantum field simulation. This is based on of quantum field theory. This is based on a paper by Stephen Jordan, Keith Lee, and John Presqu'île, which is a qubit quantum simulation paper, which is a beautifully written paper, very lucid, shows that you get an exponential speed up for quantum field theory simulation. And this has been translated to continuous variable by Kevin Marshall, Raphael Puser at Oak Ridge, George Siopsis at Tennessee, and Christian Woodbrook, now founder of Xanadu. Raphael was my second PhD student, so I'm very proud of him. This is pretty arrogant, I'm sorry. But this is, they took the idea by Jordan, Lee, and Presqu'île and translated it to continuous variables. And it's interesting because continuous variables are kind of a natural implementation of quantum fields, right, in quantum field theory. So there's a very nice match of concepts there. And they showed some quantum circuits involving squeezing Gaussian, non-Gaussian to implement the 5-4, for example, quantum field theory evolution. So with that, I'm gonna stop because I'm running very long. I'm putting some bullet points here to try to impress upon you that if you think that there are reasons why this will never work, I welcome those remarks. I'm willing to learn. I personally do not think there are roadblocks. I mean, there's a lot of work ahead. Right? There's a lot of work ahead. but this is a very exciting perspective. I know we have competitors, fierce competitors on many continents who agree with us. So it's a lot of fun. And we think the scalability problem is basically solved, but the decoherence problem is not. And that's what NISC means, right? And but also think that this is an interesting quantum technology because of integrated optics. And with that, I'll leave you on a note of wisdom from one of our luminaries. Thank you very much.
Yeah, thank you, Oliver, for the really, really nice and very pedagogical talk. And there are some more questions. And maybe let me start with the ones that were still for the first part of your talk, and then we go through, right? So there's one from David Nadlinger, and that is about your part about on the cluster state, experimental cluster state generation. And the question is, what is the biggest limitation for the number of modes in current experimental platforms?
Yes, great question. So it depends on whether you do frequency domain or time domain or even spatial modes people are looking at. So in the frequency domain, our limitation, what we do is the phase matching bandwidth of UOPO. I didn't show you that, but we measured it. It's flat top over at least 3 terahertz, which is more than 6,000 modes in our case with the 2 polarizations. We think it probably, the theoretical calculation is 10 terahertz. So it's like, okay, you know, 10,000, tens of thousands of modes. Okay. So that's you can engineer the phase matching to be even broader band than that people have done that, like AVPR has done that, and other folks have, like Steve Harris pioneered the very ultra broadband nonlinear optics. Okay, in the time domain, it goes as long as your experiment is stable. So that's the million Q mode that Furusawa does. So if your experiment is stable, you keep going and you measure and you create the cluster state and you measure it and you create it and you measure it. And it's sort of the Wallace and Gromit cartoon thing where, you know, there's this runaway toy train and building the track. They grab a box of rails and build the track in front of a train to keep controlling the thing. And it's kind of, it's Paul Kwiat who came up, I think, with that first analogy for quantum computing in the time domain. And so as long as your experiment is stable and doesn't drift, you can keep going forever. So, and then if you have what we call the musical score condition, so you work in the frequency and time at the same time, then you can use both of them as 2 dimensions. And so these can go, so Furusawa has shown 1 million modes at the same level of entanglement, right? And then the entanglement decays and then they cut it, they stopped, but they kept going for a while. So that's kind of the order of magnitude right there. So, you know, 10,000 in frequency times 1 million in time, that's 10 to the 10.
Okay. Then there was a question, actually there were a few questions around scalability, and you say that the problem of coherence is there. So let me ask one concrete question, that was, what is the major source of errors in this quantum computing scheme?
So the major source of errors, like for everything else, it's loss. Well, okay. So there's like in any quantum optics experiments, the major source of errors is photon loss. And so basically it's vacuum contaminations. I mean, like if you have a photodetector that's not 100% efficient, that means that you can actually model that as a photodetector that's 100% efficient, that's your light. And then there's a beam splitter here. As if say the real thing is 95%, well, it's like 100% efficient with a 95% transmitting beam splitter. So you lose 5% of the light, but that's not the biggest problem. The biggest problem is that you're getting 5% of vacuum in there onto the detector. And that's what the disaster is, right? And so everything has to work really well. So, but LIGO is using, and I have some in my lab, photodiodes that are 99.high% efficient, right? So, not a problem. The other thing is, okay, mode matching. If you have visibility of your interference when you do squeezing measurements between local oscillator and quantum mode, but this is defined by the cavity. So if you do your mode matching carefully, then you can get into the 99% level as well. If you get to the percent level, then you're compatible with the squeezing levels that are needed to achieve fault tolerance, according to Menikuchi's work and others now. Kosuke Fukui in Japan also has shown that this limit can be brought down to 10 dB using GKP states and CLAs. Right? So, but basically, you want to take care of losses. That's for sure.
Okay, maybe you can say something and enhance your answer. Basically, build on that because of there was a discussion about you said that the scalability problem is basically solved while the coherence problem is not. My personal
coherence. Okay, coherence means several things, right? There's
or let's say the noise problem, right? But
yeah, well, the quantum error correction, right? Who's doing quantum error correction right now? Devoré and Chilkov groups at Yale have made a GKP and SILA and quantum error corrected a qubit with that. Yeah, there's been some single qubit. Maybe John Martinez has done that too, I think. There's been and maybe on trapped ions. I don't want to omit anybody. I haven't done a thorough, but it's not been on more than one qubit, right? And the NISQ noisy intermediate size quantum device acronym has been brought up because we don't have quantum error corrected devices, right? So that's what I'm talking about. I'm talking about quantum error correction, and if quantum error correction is not doable, then that's what I'm saying. So we don't have it yet, right? But it doesn't mean it's not doable. So in principle, it's solved. On paper, the theorists have said, okay, just do this, right? So this is not a theoretical question. The GKP encoding has been figured out. Now the question is, how do you make it in the lab? So you need giant nonlinearities. The superconducting qubits have giant nonlinearities for microwave cavity fields, so they are having a ball with that, right? But integrated optics has confined light, ultra high intensity, that kicks ass too. So to be followed, right?
Okay, thanks. So there's one question from Elisabeth Goldschmidt that was, can you also make one-way quantum repeater states with the cluster state geometries you are considering?
Oh, the ones that are used, proposed by Hoi-Kwang Lo for quantum repeaters without quantum memories. Oh, yes, sure. In fact, we have, in fact, they're super easy to make with continuous variables. We have they bipartite. If you make bipartite complete states, so you have two sets of Q modes, and each one of them is connected to all the other guys. So you have a super highly redundant connectivity. That's kind of the idea behind the Hoi-Kwang Lo quantum repeater states. The thing is, though, for continuous variables, they're not really needed because everything is deterministic. Well, you still need quantum repeaters, though. But the idea of these quantum repeater cluster states is because the Bell measurements are probabilistic inherently, and so they don't always work. So you have to have a multi-try structure, which is that brilliant idea of this coherent repeater state. If you do continuous variable quantum communication, which is something I'm interested in as well, because I think we have ideas to deal with the losses, but okay, that's for another time. The EPR measurements, which are the analog of the Bell measurements, are deterministic. So you don't need to have, but you need to redistillate the entanglement to increase, right? You still need some measure of quantum error correction. That's what the quantum repeater is supposed to be doing. And so in that sense, I think you're going to need some non-Gaussian resources in there somewhere. But the cluster state, yeah, the cluster state can be done with continuous variables very easily, bottom line. Very, 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 like, it's disgusting how easy it is. But it's not really useful for continuous variables. It's useful for photonic qubits, because of a probabilistic problem of the Bell measurements.
Okay, maybe let me ask one last question, and the rest we do then in written form. So there's another one from Bill Phillips, and that's you seem to have been carefully to specify that non-positivity of the Wigner function means non-Gaussian rather than negative Wigner function. So the question is, what is the significance of the Wigner function going to 0, and does it matter how it goes to 0?
Oh, well, you know, the big deal is the Wigner function. I mean, okay, the big deal is the Wigner function. It's not, to me, it's not any different as a probability distribution going to 0. It's just a, okay, yeah, this ain't gonna happen ever. If the Wigner function is positive, if it has negative parts, then it's gonna cross the 0. Then if it's not positive, not everywhere positive. Yeah, I'm always trying to get my math right, and I'm a physicist, so thanks, Bill, for noticing. But if it's not everywhere positive, then it is not understandable as a probability distribution, as a joint probability distribution, in which case we should stop thinking about this way. Then I don't know what a 0 crossing means. It could mean something special, but I'm not sure what it is. There are very interesting things about the Wigner function, like the volume of a negativity is in Claude Fabre's language of the Hilbert space of quantum modes, or Q modes, like I like to call them. It's an intrinsic quantity, so it doesn't change if you change the mode basis, so the field superposition. So there are very, very fascinating things about the negativity, the negative parts of the Wigner function. I think it's which disappear when you look at the Husserl Q function. The Husserl Q function is so boring because it's always Gaussian. It's like, it's bland. It's not changing. You can't use it for anything. It's like, well, we use it for, because that's what we measure to do tomography. But anyway, I hope this is useful for something. Not too much of a rant.
Okay. So let me thank you again, and maybe simulate the clapping from everyone. And we are 10 minutes over time, and I give back to Sebastian.
Well, also from my end, Olivier, thank you very much for a very cool pedagogical talk that I certainly learned something from. And next week, I'd like to announce we will have another cool talk, I think, by Antoine Beauvais, who will be speaking about Rydberg atom arrays. And if you want to know more about what we're doing, please go to our website, quantumscienceseminar.com, subscribe to our email list and the Google Calendar that's available there. Also follow us on Twitter if you like. And certainly check out our sister seminar, where tomorrow they will have James Thompson speaking about superradiance on ultra-narrow optical transitions. And with this, I'd like to thank you for your interest and see you again next week, same time, same place. Bye.